Hello everyone, I am Dr. Naresh Kumar, Assistant Professor in the Department of Electrical and Electronics Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about AC emissions question bank questions. So total we have 20 questions. In that first question, explain the working principle of three-phase induction motor. Why is induction motor is so significant? So first I will explain that importance first. So why it is a self-starting device. First question, it is a self-starting device. So next, it is the construction of three-phase induction motor is very simple and rugged construction. The the cost is very less, cheapness, and next the maintenance is very less, and good power factor and higher efficiency. So efficiency is good. And so the main thing is it is a self-starting device. And what is the working principle of three-phase induction motor is rotating magnetic field and electromagnetic induction. If you give three-phase supply to the three-phase induction motor stator RYB, this is three-phase supply RYB. This is three-phase balanced three-phase supply. If you give, this is stator of the three-phase stator winding of the three-phase supply stator core, and induce rotating magnetic field RMF, revolving magnetic field, developed in the armature core, and revolving magnetic will core, that is rotating magnetic field. And this there is a rotor inside the stator. This rotor having conductors. This revolving magnetic field cuts the rotating Farad. According to the Faraday's law, it cuts the rotor conductors. This revolving magnetic field, and there is a relative motion between rotor conductor and this RMF, and induced EMF will be developed in the rotor conductor. In case of squirrel cage induction motor, the rotor bars are short circuited, and in case of slip ring induction motor, with the external circuit, it is a closed for there is a current, and this current set up the flux, and this flux, this is the electromagnet, and this is the revolving one. Here we have two magnets. Due to the interaction of this attraction or repulsion forces, there is a force. There may be a torque will be developed on the shaft. That is the working principle of three-phase induction motor. Now here, how rotating magnetic field will be developed in the stator core, so that I explained in the previous lecture. That is the working principle of three-phase induction motor. So now here, second question. So what is an alternator? Alternator is a synchronous generator, that means AC generator, which converts from mechanical energy to the electrical energy, that is AC electrical energy, that is alternator, that is synchronous generator. Now explain its construction. So first one, what is the construction here? The construction of three-phase induction, three-phase AC generator, that means alternator, it consists of stator and rotor. Rotor is rotates inside the stator, and stator carries stator winding, this one, and rotor carries rotor winding, and this one is this be depending upon the type of rotor construction. There are two types of rotors. First one is a slip ring rotor, slip ring induction, slip ring alternator, and next second one is the projected type. So salient pole and non. This is the salient pole. So salient pole, non-salient pole means that is cylindrical type. Next, not slip ring. Sorry. So why stator core of alternator is laminated? To reduce the eddy current losses, we will use laminated construction of three-phase stator core. This core is laminated. So if core is because of the core, so there may be a losses. That losses, to reduce that losses, we will use laminated construction to reduce the eddy current losses. So now here, the working principle of three-phase induction motor I explained in the previous slide. If you give the three-phase supply to this, and RMF will be developed. This RMF cuts the rotor conductor, and induced EMF will be developed, and that induced EMF cuts the it is a closed path current setups, this current setup, the flux, this flux, and this RMF and induced EMF, mechanical energy will be developed. Can the rotor run at synchronous speed? No, it cannot be run at synchronous speed. So ns equals to 120 F by P. Justify your answer. It cannot be. So if it is equals to ns minus nr, if it is equals to, there is no slip. So there is no relative motion between that rotor and that rotating wire. This ns means rotating RMF. This RMF, rotating magnetic field, will be developed. That speed equals ns 120 F by P. If rotor speed also same, so there is no relative motion between RMF and this rotor, and there is no flux cutting. Flux cuts the rotor conductor. There is no induced EMF according to the Faraday's law. What is Faraday's law? Is directly proportional to the d phi by dt. There must be change in flux d phi by dt with respect to the time. So if it is equals to synchronous speed, that rotor speed, so there is no relative speed. So it is equals to 0. That speed is 0. The speed difference is 0 means you can speed difference is 0 means there is no induced EMF. This EMF is 0 means there is no force on the rotor. So rotor is at rest position. So that is next. Fourth question. Give the constructional details of alternator. So this I explained in this. So first, this stator, rotor is salient pole. This is salient pole construction, and non-salient pole means that is cylindrical. This is the stator core, carries the three-phase winding, and this three-phase winding, and this rotor is also carries the rotor winding. Here you can give the DC supply to this rotor, and it gives the DC supply. And there is a magnetic field setups, and rotor rotates, and this stator, this rotating magnetic, this rotor current setups the flux. This flux cuts the stationary conductors, stator conductors, and induced EMF will be developed. So that I explained in the previous lecture, construction and working principle of alternator was that lecture. Next, discuss how torque is developed in the rotor of the induction motor. Same thing here, same question. So this is rotor, stator, three-phase supply, RYB to the three-phase winding, RYB connect this one, and RMF will be developed. This RMF cuts this rotor conductors, EMF will be developed. It is a closed path, and current will be set, current flows in this circuit. This current set of the flux. Due to this interaction of this RMF and phi, there may be a mechanical force. So in that way, torque will be generated. Mechanical force means that is torque. Torque developed in the rotor on the three-phase induction motor. This is three-phase induction motor. Next question. Discuss how torque is developed in the three-phase induction motor and how it will be affected. So that one. Describe the working principle of three-phase induction motor that I explained. Explain the effect of slip on the performance of the three-phase induction motor. So now here, this one. So T is directly proportional to the I2 cos phi 2 and next phi 2. So phi is directly proportional to the E2. So now here E2 equals to S into E1 and I2 equals to that formula. So this, it is depending on the slip only, say rotor induced EMF, and I2 equals to cos phi 2 equals to, that equals cos phi 2 is R by Z, that equals to R is, there is no effect on the resistance, only reactance, square root of R2 square plus S into X2 whole square. Depends on the reactance. Why? Because here, so there is a X2 means 2 pi F CFL. So there is a frequency. Rotor frequency is very small. So that is depending on the F. R equals to S into F. That is depending on the supply frequency. Same way here E2 by S into E2 by Z2, that equals to S into E2 divided by square root of R2 square plus S2 X square into X square. So So now it depends slip effect on reactance, power factor, rotor current, and rotor induced EMF. Next, describe the constructional features of both slip ring and squirrel cage induction motor. So constructional features means it is looks like a cage type. So now it is a star connected like this. The diagram, this constructional details I explained in the previous lecture. So first I will discuss the merits and demerits of squirrel cage and slip ring induction motor. So slip ring induction motor. So first slip ring induction motor and squirrel cage induction motor. Depending on the rotor construction, if it is rotor is slip ring, so that is wound rotor, that is a slip ring motor, and if it is a cage type of rotor, means squirrel cage type of rotor, that is slip ring squirrel cage motor. So now this is more depending upon the type of. So it is a cylindrical laminated core parallel slots here. So here slots are not parallel. So skew type here. So this one is skew type. And here the another name is phase wound, and this one is a cage motor. And this construction is complicated. It is a simple and rugged construction and added external to the rotor, and rotor bars are here. So here this rotor bars are closed here with the help of external resistance here. Both rotor bars are short circuited with the help of end rings here. So here rotor resistance starter can be we can use, but here rotor resistance starter cannot be used. And here for high starting purpose we will use this one, and for low starting torque purpose we will use this one. And then here brushes are present, here brushes are absent, and here efficiency is very less here and efficiency is very high because of this resistance we are introducing. Losses are less and losses are high, efficiencies high efficiencies. Here 95% of induction motors are squirrel cage and 5% of induction motors are slip ring induction motor. Only for high starting torque purpose we will use. Explain in detail the constructional features of three-phase induction, three-phase alternator. So constructional features I explained in the previous slide. Mention the types of induction motors, same slip ring and squirrel cage, this one. I explained in the previous slide. Describe in detail constructional features of alternator, three-phase alternator. So this one is also explained. The working principle of alternator. How it will works. So how it will works. So this is a stator. Stator carries the stator winding, that is three-phase winding RYB. So now here from this you can get the electrical power, that is three-phase electrical power. And next here is the rotor is here. This is the rotor, salient pole rotor, and next here the winding. So the winding is here. So stator winding, this rotor winding is given to the DC supply. So what will happen here? If you give DC supply to the salient pole rotor winding here, so current flows in this. So this current set of the current flows in this, and this current set of the flux. There is a flux. So this flux is rotating inside the stator, and here stator conductors are stationary and flux is rotating. And flux is rotating means E is directly proportional to the d phi by dt according to the Faraday's law of electromagnetic induction and dynamically induced EMF. What do you mean by dynamically induced EMF? There must be relative motion between conductor and magnetic field. Here conductor is stationary and flux is moving. So there is a relative motion between them. So flux cuts the conductor and induced EMF will be developed in the armature conductor. According to the Faraday's law of electromagnetic induction, E is directly proportional to the d phi by dt. And this induced EMF we can give the here. This rotor is rotating, and this rotating means that is mechanical energy, and we are getting the electrical energy at the three-phase winding, that RYB terminals. In this way, three-phase electrical supply will be generated at the rotor winding. Now, the calculation and voltage regulation of synchronous impedance method. So, what do you mean by regulation? Regulation is also from no load to the full load. So, E2 minus V2 divided by V2 into 100. This is for any machine, percentage voltage regulation equals to from the no load, and this is the full load. No load condition measure the voltage, and full load condition measure the voltage. If you substitute in this, you will get the regulation. So percentage voltage regulation can be calculated with the help of synchronous impedance method, that is EMF method, and another method is the ampere turn method, that is MMF method, magnetomotive force method, and another method is a Portier method. That method is that one. So the total three methods. So first, here synchronous impedance methods. In the synchronous impedance method, we need, so here Z equals to, first Z equals to square root of x2 square, x2 square equals to r2 square, x2 equals to square root of z2 square minus r2 square. So this one. So now here R2 is calculated from the DC resistance test. And this Z is obtained from the OC test, open circuit test, and short circuit test. So here Z is can be calculated. These are the open circuit characteristics are drawn between field current versus and this one and induced EMF. So EG. And next, another characteristics, short circuit. This is open circuit test. This is short circuit test. This is calculated from armature current versus field current. So now we should draw the vertical and A, B, C here for the same some fixed rated time. This AB by BC is known as this impedance. After getting impedance and R2, you will get the X2. And there is a formula E2 equals to V2 minus V2 plus and I2, if you know the current I2, and Z2 equals to R2 plus JX2. This is the formula. So now in this way, the regulation can be calculated using synchronous impedance method. To perform this synchronous impedance method, so you need to conduct three tests. First one is the direct resistance test, open circuit test, and short circuit test. Next, discuss the various losses takes place in the induction motor. So what are the losses here? And effect of the slip on the performance of the slip. So this I explained. So this is effect on the cos phi 2, power factor I2 in the current and in the E2 and in the reactance also. So this will be effect on this one. So what are the losses here? So now here there are stator losses. So if you give input and there may be losses. If you give input to the electrical energy to this stator, and there may be a losses, stator copper losses and stator iron losses. Stator copper losses and stator iron losses. And next, if you give this, after that it is given to the rotor. Rotor also there are copper losses and iron losses, but here rotor iron losses are very small because rotor frequency is small. Here this core losses, iron losses is divided into two parts: hysteresis losses and eddy current losses. These losses are depending on the frequency only. This frequency is very less, means these losses we can neglect this one. Eddy current losses and hysteresis losses we can neglect this one, means we can neglect the iron losses, core losses, we have only copper loss. After that, there may be a windage losses here, windage losses and air frictional losses. Now, here, next, mention the reason for rotor of polyphase. That means three-phase induction motor can never attain synchronous speed. This I explained, discuss. So mention the reason, proper reason. So now here, this is same thing, RYB here. So now RYB. If you give three-phase supply to the stator winding of the induction motor, rotating magnetic field will develop. The rotating magnetic field speed is Ns equals to 120 F by P. That is synchronous speed. So motor can never attain synchronous speed. So what is the reason here? So first here there is a inside the rotor. Rotor is stationary. Initially it was stationary. So it is rotating magnetic. There is a relative motion between these two. So now here, if there is a relative motion between these two and E is directly proportional to the d phi by dt according to the Faraday's law of electromagnetic induction, and induced EMF will be developed in the armature conductor, rotor conductor. And now here it is a closed circuit for squirrel cage and for slip ring, and current flows, and this current setups the flux, and due to this interaction of this RMF and this electromagnet, and there may be torque. But here if it comes to the, this rotor is also comes to the ns synchronous speed, but there is no relative motion. So motor automatically stop. There is no relative motion means there is no induced EMF, there is no current, there is no flux, there is no interaction of rotating magnetic field and this electromagnet. So that is important. So the reason for the rotor of the three-phase induction motor can never attain synchronous speed. So it never attain synchronous speed, that equals 120 F by P. 14th question over. Next, 15th question. Discuss the constructional features of both slip ring and squirrel cage induction motor. This I explained the construction of three-phase induction motor for squirrel cage and slip ring also I explained. Watch that lecture. So now here, 16th question. With a neat sketch, discuss the principle of three-phase induction motor. I explained, no problem. Now briefly explain the torque slip characteristics of three-phase induction motor. Torque slip characteristics here. So torque, this is torque and slip. So there are two slips. Torque is directly proportional to S into E2 square into this one R2 square in plus S x square for low slip region, and for high slip region. So for low slip region, torque is directly proportional to the S. So now for this one, start from here, and for high slip region, torque is directly proportional to the 1 by S, inversely proportional. In this case, rectangular hyperbole. This is the torque is maximum torque. So here S equals S, a maximum slip, and this is the T start. So now here, so slip characteristics, torque slip characteristics. So starts from here. Initially SCNS equals to 0 and slip equals to 1. Slip equals to 1 and N equals to NS, that one, slip equals to 0. Low slip rate, this is from slip value 0 to 1. Here NS equals to NS, and this one is a NS equals to 0. Next, discuss how torque developed in the, so this also I explained. Mention and interpret the difference between squirrel cage induction motor and, so this one is also explained, same thing. So for high starting and for lower high starting torque, for low starting torque we will use squirrel cage and slip ring. and construction type another name. So the difference I explained in the construction of three-phase induction motor. So watch that lecture. So this slide is also I explained we can add the external resistance to a rotor of slip ring induction motor, and we cannot add. So already rotor bars are short circuited, permanently short circuited in case of slip ring induction motor. So now here rotor resistance control is possible. Speed control is also for rotor resistance control is possible. Speed control starter. The one next. Next 19th question. Voltage regulation of alternator using synchronous impedance method. Same thing here. We will use here synchronous impedance method, that is MMF method. Another method is EMF method, that is ampere turn method, and Portier method. Another method. Three methods. So first here seeing regulation of alternator using synchronous impedance method. EMF method means to conduct that one we need DC resistance test. First one, and second one is the open circuit characteristics, and third one is the short circuit characteristics. So three methods, three tests we will perform on alternator. So here this test is drawn from so induced EMF versus from this we will get the field current, and this for the armature current versus and field current, and in this so RA we will get. So this I explained. So first here RA will, so Z equals to R plus JXL, Z equals to R square plus X square square root, and X equals to Z square minus R square. Here R is can be obtained from this, and Z is can be obtained from the open circuit test. From the this is open circuit test, and this one is the short circuit test, EG and IA, and this is the field current. So if you draw the vertical line, so from this A B C AB by AC is known as a impedance. So open circuit voltage by AB by BC, and short circuit current is known as the impedance. From that calculate the impedance, resistance and reactance. After that calculate the voltage drop from no load to the full load. Then calculate the voltage regulation of the alternator using synchronous impedance method, that means EMF method. Next, summarize briefly advantages and disadvantages of three-phase induction motor. So three-phase induction motor already we discussed here. So these are the advantages first. Three-phase induction motor advantages. So first one is that it is a simple and rugged construction. Strong construction, simple and rugged construction here, and it requires less maintenance. It does not means less amount of maintenance is required for this three-phase induction motor. And next, efficiency is high. I already explained, and power factor is very good power factor for three-phase induction motor. Expensive, cost is very less expensive means cost is very less, and it does not require any additional any extra device to start the machine. So it is a self-starting device. We can call this three-phase induction motor as a self-starting device. So what are the advantages here? It has simple and rugged construction and less maintenance. Efficiency is high, good power factor, and less expensive, and self-starting torque. And what are the drawbacks? So drawbacks of three-phase induction motor. So first disadvantage of three-phase induction motor. First I will discuss this one. So it operates under low power factor. So that power factor range, power factor means cos phi. Cos phi range is always -1 to 1. This power factor is power 1, positive means 0 to 1. So for induction motor, this power factor range is this one is 0.3 to 0.5 lagging power factor. So induction motor operates under lagging power factor. During the light loads, they operate at very worst power factor condition. So this is one drawback. So lagging power factor, it operates under lagging power factor. And next, here, so first one, so this one, here a three-phase induction motor at so constant speed. So if they are constant speed like shunt motors, so constant speed motors means speed control is very difficult. If almost speed is constant, means speed control is very difficult to control the speed. And next, three-phase induction motor have poor starting torque. Starting torque is very poor and high in rush current, about 4 to 8 times of the rated current. So low starting torque. So squirrel cage induction motors having low starting torque, but slip ring induction for high starting torque purpose, we will use slip ring torque induction and low starting current. So here this more 95% of the induction motors are squirrel cage induction motor. So here they mention low starting torque and high inrush currents. So total 20 questions completed. I hope all the 20 questions are clear to you. If you still have any doubts in this lecture, you can comment in the comment section below. I will answer to your queries. Thank you. Thank you very much to you.
Like, share and subscribe. Hit the bell icon for more updates.